All right. Hi, guys. So I guess I sound a little more cheerful now. So this is AP Chemistry, topic 8.1, Introduction to Acids and Bases. Next slide. So today's objective is to be able to calculate the values of pH and pOH based on something called Kw and the concentration of all species present in a neutral solution of water. So a couple of essential knowledges you need to be mindful of. So a couple of equations. So pH is negative log of the hydronium ion. pOH is negative log of a hydroxide ion. When you may hear me say hydrogen or hydronium ion, and those are pretty much interchangeable. So hydrogen is H plus aqueous, and hydronium is H3O plus aqueous. It's preferred that you use hydronium and H3O plus, but they will also accept H plus. So this K sub W, that is an equilibrium constant regarding water. So excuse me, it will if it's pure water, you may have something called a neutral solution. It's going to be at 25 degrees Celsius. That's what we're looking at. So the pH and pOH will be 7, etc. The pK, so the P of the pKw, or the P of the equilibrium constant, will equal 14 because pH plus pOH. So the values that you can see for the equilibrium constant for this is dependent on the temperature. So if it's anything other than 25 degrees Celsius, it will deviate. Oops, forgot the sound effect. So in unit 4.8, we were looking at acids and bases. Reminder that a Bronsted-Lowry acid is a substance that donates a hydrogen ion, and when it interacts with water, it's going to form the hydronium ion, the H3O plus. If it's a Bronsted-Lowry base, it's going to be the one that's accepting the hydrogen ion. So when we look at acids and bases, we look at their pH, and it's a way to describe how something acidic or basic something is. To calculate the pH of a solution, take the negative log of the hydronium ion, and if it's the pOH, it's the same concept, but it's only if you're looking for the pOH. Use the same type of equation, negative log of the hydroxide ion. But if they give you the hydroxide ion and they want the pH, you got to do something else with that. So the equilibrium constant for water can be written the following way. So you have two water molecules forming hydronium ion and also a hydroxide ion. So your Kw for that would be Kw equals the hydronium ion times the hydroxide ion. If we are at 25 degrees Celsius, so the Kw is going to equal 1 times 10 to the negative 14. Pure water is neutral because you have an equal amount of, or equal concentration, of hydronium and hydroxide ions. So this is something to kind of keep in mind when you're at 25 degrees Celsius, how to solve for your hydronium, hydroxide ions, your pOH, your pH, etc. So this is something you need to keep in mind. I guess I got that sound effect too. Okay. So, keeps you awake, hopefully. So you see the general trend as you are increasing the temperature. Look how much the Kw changes, and therefore your pH will change for being considered neutral. So 7.472 is about 0 degrees Celsius, and then you'll see how at 20-ish, 25 degrees, 30 degrees-ish, it's around 7, 6.9, and then if it gets hotter, the neutral pH is actually going to change, and notice how so does the concentrations of the hydronium and hydroxide ions. So looking for significant figures for pH, something to be mindful of. You are focusing on the numbers after the decimal point, and those are considered the significant ones. This is because the value before the decimal point, called the characteristic, is really a description of the order of magnitude of the number. So if you have 7.010, that's 3 sig figs in terms of the pH. A way to remember when a substance, for something to be considered a strong acid or base, it needs to dissociate or ionize completely. So your strong acids and bases are listed. You have HCl, HBr, HI, HNO3, H2SO4 for the first hydrogen ion, and HClO4. Strong bases are the group 1 and group 2 on the periodic table. So sodium, rubidium, strontium, barium, calcium, cesium, lithium, and potassium. So those are the ones that ionize completely when they're put into solution. So that means that they won't have an equilibrium constant because they are completely dissociated. What is the molarity for the hydronium ions in the following solutions at 25 degrees Celsius? Determine if they're considered acid or bases. So you can kind of tell that. So the pH, so how do we solve for the molarity? So the hydronium ion, or the H+, let's do hydronium to be consistent. So it's 10 to the negative 3.689. Oops. So this is going to be, because of 3 sig figs, 2.05 times 10 to the negative 4. And my pH is 3.68, so I have an acid here. My pOH is 6.410. So to find the pH, it's 14 minus the pOH. 14 minus 6.410. This is 7.590. 3 sig figs at the end. So 1, this is a base because my pH is above 7. So to find the concentration of the molarity, H30 plus equals 10 to the negative 7.590. And that's going to equal 2.57 times 10 to the negative 8 molarity. Oop. Yes, molarity. Oh, my bad. All right, so I have a hydroxide concentration of 1.56 times 10 to the negative 4. So one of the equations we're going to use to find my hydrogen, or my hydronium ion concentration, so H plus, or hydronium ion, equals 1.0 times 10 to the negative 14 divided by 1.56 times 10 to the negative 4. This will give me my hydronium concentration of 6.4 times 10 to the negative 11 molarity, or molar. So how to find out if this is considered an acid or a base? You need to take the negative log of this concentration. So remember, your negative log of the hydronium ion will give me my pH. So negative log of this, wait, where is it? Negative log of 6.41 times 10 to the negative 11 is 10.193. That's my pH, just so you know, to find out that this is considered a base. Okay. Alrighty, so pause the video, work on this. This is something that you should be able to do once you get the hang of it. Actually, no. I'm going to do, what is the dissociation equation for this reaction? So you have a weak acid. So the dissociation equation is going to be the weak acid in its aqueous plus water producing hydronium ion aqueous plus my my A minus. So write the Ka expression. Okay, now you can pause the video and then you can do this by yourselves. So to find the Ka expression, Ka, remember that it doesn't involve liquids or solids, so it's H3O plus the concentration times the A minus concentration divided by the concentration of the weak acid, whatever that will be. So calculate the concentration of the hydronium ion. So to find out what that is, so the weak acid itself has the weak acid is 0.1000 molar. The pH of the solution is 3.456 in the end. So you can define the hydronium concentration. You are going to take 10 to the negative 3.456. So it's 3.50 times 10 to the negative 4 molar, or molar, if you want to call it that. So complete a nice diagram to find the Ka. So the K sub W is for water, for A, and K sub A, K sub B, it's going to be for acid and base respectively. So you have your weak acid, your double arrow, H3O plus, the concentration of A minus. So my initial concentration is 0.1000 molar. It tells you that, that at equilibrium, we're going to end up having a pH, the concentration of the hydronium ion is going to be 3.50 times 10 to the negative 4 molar. That means that because they're in the same ratio, it's going to be times 10 to the negative 4 also. So that means I started off with 0 for these because it doesn't mention anything. So we're going to assume that's the case. So how much does this change by? 3 times 10 to the negative 4 plus 3.50 times 10 to the negative 4. My weak acid will decrease by this much because that's the ratio. So minus 3.50 times 10 to the negative 4. So when I subtract this out, I end up with 0.0997 molar. Okay, so I'm going to erase the top part now, so I can kind of finish this, because it wants me to find out what is the K sub A for this. So all you're going to do is kind of plug in, kind of like we did before in the last unit. So K sub A equals my hydronium ion times my A minus ion. So 3.50 times 10 to the negative 4 times that again, divided by my HA says 0.0997. I do my math. Remember that I have 3 sig figs according to this. Actually, hold on. That's my concentration. Yes, I have 3 sig figs. So in the end, I'm going to get 1.23 times 10 to the negative 6. All right, so if you have any questions, please let me know.